Hi everyone again. I hope you can hear me well. Um, this is the outline of my presentation. I will start with a brief introduction, very brief, and I will show 4 examples of application of intelligent optimization or intelligent techniques to support our optimization in some cases. Mainly in the management of energy consumption in buildings and also in communities of consumers and generators, like when an aggregator is considering it. So I will not go too much on the aggregator concept because it has been discussed this afternoon, but this is in fact our motivation for most of our works on the way that we can put small resources all together as a strong player, collected by the aggregator to go to a market or to efficiently manage the community. Um, and this is because we know that a lot of potential is available for demand response in the small players. And for that, we need to handle it with a context approach. So we need to adequately model the environment and the comfort and the preferences of the consumers so we can give what they want when they want uh, in order to get the response that we want as an aggregator. So um, in our uh, lab, in our research building, um, where people, our researchers and scholarships and so on, where everyone is working, we have divided our building in 3 different zones, and we have automation means that support the data collection and the validation of our demand response and other models. And this is the interface that all the users in the building they have when they arrive, and they can control and identify themselves so they can interact with the energy consumption and environment monitoring with the CO2, temperature, humidity in each room, and also control uh, lights, air conditioning, and some specific appliances that we use um, for flexible operation of the energy management. So also we have the click to control prototype that each one can access from their Android interface in their phone and tablets and so on. And this is web-based, so this is quite flexible and is the way that everyone can interact with the system and see their behavior and also give input to the optimizations that we have. And as a last, uh, the last that I will say, but not is not the last motivation for us is to collect all the data that we have in the building, store it and make it available for learning approaches like for energy consumption forecast, for consumer or user behavior learning, for intelligent decision on their preferences, because consumers most of the times they don't know themselves what they want, so we must learn according to their behavior. So that's why we monitor the building. And my first application will be air conditioning consumption optimization based on CO2 concentration level. I show here a prototype that we developed to control air conditioning with the Arduino. And after optimization, we in one of the approaches, we implement all the scenarios in the decision tree for the Arduino to be able to control the air conditioning, because Arduino is not able to run the optimization. So we can take local decisions and according to the environment. So you don't need to have Arduino connected to the internet. In some applications you don't have it, so that's a motivation for us. This is a profile that we have, and with some earlier results on the schedule that we have in the building. So this is the reduction that we have in each light. So we have 20 lights in our rooms in this building, and we are controlling each one. And also we can see for each period that we are controlling the energy consumption in a day, and for each single light, what is the actual consumption that we have. So for you to see that all single lights are controlled there and monitored. And in this model, the optimization consider that you have in the objective function the consumption of the air conditioning, each room. So it's one appliance in each room in each period, and you have also the CO2 concentration that you are measuring also in each room in each period. So we want to minimize this product. So we will use the CO2 concentration as a priority signal to indicate which air conditionings will be shut down in some moment for the whole building to attain required reduction level. So if in the building we are requiring some amount of reduction for a demand response event from the exterior, or to meet the PV generation in the building, so we can specify how much we want to reduce, and the algorithm will select the most interesting air conditioning appliances in each moment according to the CO2 concentration. And also we have here the relation between, we have modeled the relation between the CO2 concentration and the fact that each AC is or not working. And we have the boundings of each variable that we can actuate. And we have implemented here PSO for the optimization, as we have a lot of scenarios. In fact, we don't have a very complex optimization problem, but we want to run a huge amount of scenarios that then we want to encode in the decision tree. So I will not go in detail on the PSO. And coming back to the scenario, but this time with the PSO parameters, we have tested different tuning figures. So the number of iteration that we have in the PSO process, also the population, and in the obtained discussion time and final load, we have selected these two approaches as our PSO final model. to then run all the scenarios. So with less iteration and less population, we found that we could be quicker and have the lower final load. So as a combination of that, so that was important for us, that we keep in low iteration and we have good result. So I will not go too much in detail, but this is about the way that we collect the air conditioning, the concentration of CO2, and the way that the air conditioning being on will affect the CO2 concentration. So we have been measuring several points from our sensors, where we have the actual consumption of the air conditioning and the actual CO2 concentration. So we collect all the points. These are different rooms, and we get the equation of the regression that matches these points in each room, and this will be the parameter that we use in the objective function for each specific room. And as you see, this is a very important point, that where we can say real monitoring in a real building is very important for us. So we don't need to model the walls and the thermic behavior of the room. So this is actual measurement that will in the end represent our actual building. So, and we obtain in different periods different CO2 concentrations, and also we defined the required reduction in each period. In the first periods we have 300, then in the third 500, and finally 700. And we have implemented 2 scenarios, and for the 2 scenarios we found the schedule of the air conditioning 1 and 2 in the 4 periods, and we can see that the total reduction in air conditioning 1 is lower in scenario A, while the air conditioning 2 is lower in the scenario 2. So this is the way that we can add more complexity to the model when comes the time to decide what is the air conditioning to turn off. Also some comparison more on the 2 scenarios, more on the energy side. I will not go in detail. And coming now to another application, that is defining the optimal number of demand response programs and tariffs using clustering methods. Now we are on, let's say, on the grid side, on outside the building, collecting different buildings. This is the overall picture of a work that we published some years ago, and we have been working further on that basis. Those results have been used for other works, and in fact our challenge is to find where to put each consumer according to its characteristics when making groups. So usually, as you are a domestic consumer with, for example, 6.9 kVA contracted power, you will be in the same group of all the guys like you. But we know that you and your neighbor, even if you are the same contracted power, you have different um, preferences or comfort requests. So according to different parameters, we want to put people of the same characteristics together, not just because they are of the same type of consumer, let's say. So then we will define tariffs for these groups according to the consumers that they are there. And also it can be applied to distributed generation and prosumers. So one question for us is how much groups we will define, because in some application, if you have 20,000 consumers, in the end, you can make 20,000 groups that each consumer will have a specific tariff just for him, or you can have just another limit, just one group where just one tariff you have. But okay, this balance between having more or less groups, that will make the aggregator have more or less number of tariffs or demand response programs in the end. This is an important decision. And in this work, we have approached to apply the methods existing in the literature for optimal number of clusters determination. So that was the motivation. And to generate the scenarios, this is the optimization that we did to schedule the consumers in the presence of a demand response event, or in a context that the DG there is also dispatched. So I will not go in detail in this objective function, but we have in a scenario all the DG, so we can schedule how much distributed generation you will have in each unit. Also, how much energy it will come from the grid, from different suppliers, and also the demand response, where you give some payment according to the reduction to that consumer, or for some consumers you give a price signal that you give an increase in energy price, and it will cause a reduction in the consumption according to the elasticity parameter. And also we have the balance equation, so the consumption and generation in each moment must be the same amount. So, and we have the limits for each variable. So we cannot go use more DG than what they have available, because most of them are based on renewables. And also for each consumer, we have the maximum amount of demand response that you can use. Here comes the elasticity that I say. This is elasticity is a parameter that are available in tables. So this is a parameter. Then you have the initial cost of energy and the initial consumption. So if you apply a change in the cost of energy, consumer will react and reduce the consumption if you increase the price according to the elasticity. And also we have this aggregator want to bound the contribution of a demand response program, specific program within all the programs contributing. So we, among many clustering algorithms that we used, we have selected in the end k-means to make the clustering. And this is a network of a little bit more than 20,000 consumers and 548 producers. Some of them are prosumers, so they are consumers with DG in their house. And we have some characteristics for them, and we have defined it as they are usually initially of 5 types according to their contracted power. Then we will organize them in groups, and we want to test in the first scenario the making clustering for working days. So it is for Monday to Friday, then for weekend, and for the whole week, because this is another discussion for us. If you make groups and you want to curate groups, would you put or not weekend separately? And the optimal clusters coming from different methods, the elbow, silhouette, and gap statistic method. Here in scenario 1, we have in some method, it's obvious that what is the optimal number of clusters that the method is proposing. So here we have 9, 10, but in other methods is not easy. So, but this is some information that we can combine all the three together. For their nature, they are providing different solutions, but we didn't go in detail with that. Then coming to the scenario 2, where we have weekend days making the clustering. Now we silhouette method say should be 2 clusters. In the gap statistic, we still have 9, and also in the elbow method, it has been changed. In the scenario 3, we still have 2 on the silhouette, and now we have 10 in the gap statistic method. So we don't have a final answer to the question, what is the ideal number of groups to make, but okay, this is something that instead of just saying to the aggregator, here you have the results, just choose, we can provide some additional details for him to choose. And according to the different methods in the different scenarios, this is the amount of remuneration that the aggregator will pay to each to all the consumers and distributed generators there. Now coming to the real-time approach for demand response tariff definition using decision tree, I will speed up because this is in sequence of the previous one I shown. And here, as after we had this optimal number of clusters, we want to discuss or to provide support of decision with decision trees, because again, we had some large scenario, and we have the results and the aggregation groups that we find for the different scenarios, and also the remuneration tariffs that corresponds to the price, the maximum price that you find inside each group. And our motivation here is, when a new consumer come to the aggregator, will you need to run again all the optimizations for all the scenarios and so on? No, we will have a decision tree that will support the aggregator to easily say, okay, according to these characteristics, if this or that characteristic is in each amount, we will define in each in what group to put the consumer. And of course, here we have the respective remuneration. In this case, we have put all the consumers together, and this was the result. But we wanted to put maybe more accurate trees by separating the consumers since the beginning. And the consumers, when we are testing, we find 5 consumers to try to allocate them. to the community, let's say. Consumer 1 and 3, they have been allocated to the group number 3. Consumer 2, it came to group number 4, and consumers 4 and 5 came to group number 5. So yeah, this was a practical application of the decision tree, as we are always concerned about how our aggregator can have an easy job in his life. So he knows that a lot of demand response potential is available, but determining what is the tariff or the incentive to give to each consumer, how to group them, and so on, is not easy. So those were tools that first supported the demand response at the building level to collect the amount of demand response they need, dispatched by the aggregator, for example. Then how the aggregator handles the definition of the tariffs and the inclusion of new consumers coming to the community. And now finally we are coming to the differential evolution optimization for a residential demand response application. So here we have a battery in a house. So this consumer, he has a energy storage system and PV on the rooftop. So in order to integrate the PV in the house, he has an inverter, and the inverter inside he has 3 controllable loads. So he has 3 relays. In fact, we wanted to come to the reality. Of course, people sometimes say, okay, this is a toy problem. But the question is, we have been handling, as João and Fernando show, we have knowledge to apply to a lot of variables, a lot of consumers, a lot of decisions at the same time. But in the real world, this is one of the top state-of-the-art inverter that you can have in your house. And in the real world, we just have 3 relays to control loads. So in this manufacturer, let's say. So we wanted to come to this level, and again, this house owner will not have a license for linear programming to take decisions, and we wanted to run the PSO that then you find the parameters to take decisions inside, and when, according to the prices of electricity from the grid, according to the state of charge of the battery, according to the actual PV generation, what loads you will turn on and off, and or charge the battery. So in the end, we want to minimize the energy bill and also the cut of load consumption, because of course, if you turn off the load, of course you don't need to pay for that consumption, but we want to minimize also that load curtailment, let's say. So for the energy bill, we consider the energy coming from the grid that you need to pay, and also the energy that you are sending back to the grid, that you will receive some money, and you need to consider all the time conversion for kilowatt hour, because here you are not just considering power in that slice of time. And also regarding the curtailment, we have the three relays, as I said, and also binary variables that you can turn on and off the relay. And this is a challenge because this is not a continuous value. So you just have two options, 0 or 1. So this will make the problem harder. And then we need to have the energy balance in each moment. So again, in each moment, what you get from the grid, from the PV, from the battery, charging or discharging, and from the load must be balanced. So generation must match the consumption. And also along the day or along the simulation, we need to consider that the battery will be charging, discharging in different periods. So specific constraints are needed for that, which make the problem more complex. And in fact, we have been trying for different days, because we cannot, we should not consider that in the end of the day, the battery level is not important. Of course it is. So we consider the other day again, and in the end we should consider many days together, making the problem even harder. Then I will not go into details about the encoding and so on of the variables for the optimization, and also in the evolutionary details, I guess Fernando and João have been explaining these processes a lot. Anyway, we will be happy to give you more details on that. And this is the final schedule of our loads, actual consumption, the energy charge in green added to the battery, also the energy discharging from the battery in each moment. And of course, when you are charging, you cannot discharge. And this is the final consumption in the house. Also, we have some different convergence behavior for the different methods that we tested. We had the PSO, the differential evolution, and the third one, and for 510 individuals. So this was my presentation, and thank you for your time, and I'll be happy to answer your questions.